State and prove the addition formula for Jacobian function Jn of x, or prove that another way is to write the same sentences Jn of x plus y, that is Jacobian function, sorry, Bessel's function, which is summation n running k running from minus infinity to plus infinity Jn minus kx plus into j ky. That means it is the addition formula regarding this Bessel's function. So to find the proof of this, to write the proof of this, we use that generating function for Bessel's function we have did. So in the previously what we have did is we know that e power x by 2 into t minus 1 upon t is equal to summation n running from minus infinity to plus infinity Bessel's function at x into t power n. We have proved this one. So this is known as a generating function. This will generate this Bessel's function. So that's why it is called the generating function. So the generating function of this Jn of x, using that we can write down the generating function of Jn of x. You can have e power x by 2 into t minus 1 upon t into e power y by 2 into t minus 1 upon t will gives you summation n running from minus infinity to plus infinity Jn of x into t power n into summation minus infinity to plus infinity Jn y into t power n. Now here we can use the Cauchy product. So this is again a double series is there. So that's why it is summation n running from minus infinity to plus infinity, and then summation n running from minus infinity to plus infinity. Since this index I want to change, so that's why I'm writing this is k running from minus infinity to plus infinity. And it is as I have talked that an and bn is there. When you want a Cauchy product of that, it has to be n minus k bk, and then another summation is there. So that is the thing, that is Cn which we have. So here it is n minus k. So that is the things this is there. So that is n minus kx into jky and into t power n is there. So this is the first equation I can say. This will be the first equation. Now let us simplify this side and see what is happening. So now e power x by 2 into t minus 1 upon t into e power y by 2 into t minus 1 upon t. This is equal to e power. If I make this exponential power, so become addition x plus y by 2 into t minus 1 upon t. And if you can use that generating function here also, then this is summation as for this, when this quantity is equal to this one. So where we have x here, so here it is x plus y. So according to that, we can write down this is summation n running from minus infinity to plus infinity Bessel's function at x plus y upon into t power n. And if I call this is equation 2, and if I compare this equation 1 and 2, With this we will have, so comparing equation 1 and 2, we get, that means if we compare the coefficient both the side of t power n, comparing 1 and 2 means we can compare the coefficient of t power n. So that will gives you this equal to this one. That means j n at x plus y, that is the addition of these two, will gives you summation n running from minus infinity to plus infinity jn minus kx into jk y. So that was the things to prove. Now, based on this formula, we have some certain examples. So let us discuss that examples here. So prove that J0 at x plus y equal to J0 x J0 at y minus 2 times J1 at x J1 at y plus 2 times J2 at x J2 at y and so on. And hence, using this, prove that the first one, 1 is equal to J0 of x square plus 2 times J1 of x square plus 2 times J2 at x square and so on. And the B, that is mode of J0 is less than or equal to 1 and Jn at x is less than or equal to 1 by square root of 2 for n running from 1 to up to so on. So this is the things which we need to do. So let's try to prove this statement. So first of all, the question was to find out what is J0 at x plus y. So we know that Jn x plus y is this. So we will use that one here. So the addition formula, this is known as the addition formula. Addition formula of Jn x is Jn x plus y is equal to summation k running from minus infinity to plus infinity Jn minus kx at j ky. Now here n equal to 0, so let n equal to 0 we can put. So j0 at x plus y will gives you k running from minus infinity to plus infinity j minus k at x and jk at y. This is the things we have, and I can separate this summation to plus sign and negative sign, so that we can have summation k running from minus infinity to 0 j minus kx j ky plus summation k running from 0 to infinity, or I can say 1 to infinity j minus kx jky. So to write down this is in separately for negative index and positive index. Now if I replace this k by minus k into the first summation, so that means I need, okay, let us take this as a minus 1 and this will as a 0. So I just replace this k by minus k into the first summation. So replacing k by minus k in first series, we get j0 at x plus y equal to summation k running from 1 to infinity. Now because we have replaced k by minus k, this is 1 to infinity. This is minus, this will become plus. So jkx and jk minus y plus summation k running from 0 to infinity j minus kx jky. Now we know this relation of Bessel's function, that is j minus nx is equal to minus 1 raised to n j nx. So using this j0 at xy will be summation k running from 1 to infinity jkx, and this j minus ky will written as jky into minus 1 raised to k plus summation k running from 0 to infinity. Here is also we can use that jkx and jky is there. And if you can write down both this term combinedly, to writing this both the term combinedly, this is nothing but the summation. This is start from 0 and this will start from 1, and both the terms is same. So I can just separating out the terms which are having the 0. So that is j0 of x into j0y plus summation k running from 1 to infinity. But that summation will come two times minus 1 raised to k jkx jky. And hence we have done what we need to prove. That we have to prove that j0 x into j0 of y, and this series will have this, which is having the alternating sign. That means if I expand this one, we achieve what we have. So therefore, what we can write, j0 at x plus y will be j0 at x, j0 at y minus 2 times j1 at x, j1 at y plus 2 times j1 at j2 at x, j2 at y minus 2 times j3 at x, j3 at y plus so on. Now what was the second thing we need to prove is this. That means 1 equal to this quantity. So since I need the square here, it means that this both quantity has to be same. So x is equal to y. When x is equal to y is there, we will have this. But then this will be a 2x. So I will not get, if x is equal to y, if I substitute, I will not get this. But here on this side, we will have a 1. So that means this has to be 1. And we know that regarding j0 at 0 is 1. We know this property. j0 Bessel's function at 0 is 1 with order 0. So that's why we'll substitute y equal to minus x into this. So if I substitute y equal to minus x, this will become x square. And we use this also, the another formula that we have. That is j minus n x. Sorry, j n minus x. Regarding this, we also have a one thing which we can use. So now by replacing, by putting y equal to minus x, we get j0 x minus y, x minus x, which is j0 at 0, equal to, this will be gives you j0 at x, j0 at minus x, minus 2 j1x, j1 at minus x, plus 2 times j2 at x, j2 at minus x, minus 2 j3x, j3 at minus x, and so on. Now note that what will be the Jn if n is odd and n is even? That means Jnx. So this we have to note. Note that this Bessel's function is an odd function if n is odd. Why? Because we know that Jnx is equal to summation minus 1 raised to n upon n factorial into n plus, sorry, n is already used, so k into k factorial plus n plus k plus n factorial into x by 2 power 2k plus n. Now this n is an odd, then this is odd power of x. So if I can replace x by minus x, then minus sign will come out. So I can say that Jn of x is odd function if n is odd, and Jn of x is even function if n is even. Again the same, if this n is even, then this is even number. So x power even number, if it is negative power is there, it will become positive. So if this Jn of minus x is there, then it will give me a positive sign. So that's why the Jn of x is an even function if n is even. So here, according to the alternating sign will come out. That means here for J0 of x, the 0, if I substitute in place of 0 here instead of n, we'll have x power, even power is there. So that minus x will become same. So we can have that J0 of x, sorry, J0 at 0 will be J0 at x into J0 at x. For J1, 1 is an odd number, so that's why this minus sign will come out. So that's why this is minus minus become plus 2 times J1x into J1x. Then it is J2, but it is an even number, so it is an even function. So the sign will not be changed. So it is plus 2 times J2x into J2x. And similarly for the J3 is also we have the same thing. And if you can write down, this is in separate form and using J0 at 0 is 1, that you can see from this formula itself. If I have put x is equal to 0 here and n is also 0, then this is x is 0, so this quantity will become 0. So only the term will get is when k is 0, because this summation is from 0 to infinity. So when is a constant term is left, and the constant term is 1 itself. So therefore we can have, using this we have this J0 of x square plus 2 times J1x whole square plus 2 times J2x whole square, and so on. All of them will have. The next things we need to prove is this, that is J0 of x is less than or equal to 1 and Jn of x is less than or equal to 1 by root 2. Now J0 of x, it is easy to see that it is less than or equal to 1 due to this. Because from this what we can write, so to prove the B now, we can say that J0 of x square is always less than or equal to this. So I can add this all numbers, these numbers I am adding. So definitely all of them are a positive number, so I can add them, no problem with that because of square. So here we have this, and this quantity is 1. So that's why this we can say that J0 of x square is less than or equal to 1. So I can write down mod of J0 of x is less than or equal to 1. So that we will have as a one quantity. Now the second quantity that we need to prove is Jn of x is less than or equal to 1 by root 2. So for that, let us fix, let any fixed n belongs to n. Let us consider n is a fixed number, and need to see what is this J n x whole square 2 times, and I'm adding lots of numbers here. This is already there, so I'm adding this J0 x whole square plus 2 times J1 x whole square plus 2 times J2 x whole square and so on, plus the next term will be Jn plus 1 x whole square and so on. So I'm adding lots of other numbers other than this. So definitely this portion or this side will be bigger than this one. But we have proved that this side is 1. So I can say that therefore 2 times Jn of x is greater than or equal to 1. And so therefore Jn x whole square is less than or equal to 1 by 2. And so the mode of Jn of x is less than or equal to 1 by root 2 for any x, for any n. This is there. So this Bessel's function, if n is an integer, then it is a bounded function that we have actually proved here. So this is the property of addition property of the Bessel's function. Using that, we can achieve this results. Now the next portion or next topic is the Bessel's integral formula.